Alright, so in the last video we spoke about standard deterministic Turing machines, and we said that the set of problems that could be solved by standard Turing machines are called recursive sets or decidable problems. Now, we are concerned with decidable problems only. We're not concerned with unsolvable problems. So there are different sorts of classifications when it comes to complexity of problems. The set of problems that can be computed by standard deterministic Turing machines in a polynomial time lies within the polynomial class complexity. So given an input, let's say of size n, if there exists a deterministic Turing machine that can solve this problem in n to the k steps for some natural number k, then this problem is said to be solvable in polynomial time. Okay, and let's denote the class of all problems that are solvable in polynomial time by this boldface P. Okay, so P denotes a set of all problems solvable in polynomial time by a deterministic Turing machine. So we have different variants of Turing machines. Okay, the first variant that I'd like to talk about is called non-deterministic Turing machines. So a non-deterministic Turing machine is defined exactly as its deterministic counterpart, except that the transition function is slightly defined differently. Now the transition function is a subset of Q Cartesian sigma times Q times sigma times left-right stationary. Okay, so this tells us whether it is possible for a configuration C to yield another configuration C prime. Okay, so for example, if we have that Q1, A1, Q2, A2 in some direction D, if this is in delta, this means that the machine is in state Q1. It reads the symbol A1, and that it's possible that the machine will go to state Q2 and write A2 on the tape and move the tape in the direction of D. Okay, so we're talking about possibilities here, not in terms of probabilistic weights, but just possibility in the general sense. Okay, now we denote the class of problems that are solvable by non-deterministic Turing machines in polynomial time by NP. Okay, so NP is the class of problems solvable in polynomial time by non-deterministic Turing machines. Okay, so any deterministic Turing machine can be simulated by a non-deterministic Turing machine. Okay? If a problem is solvable in polynomial time by a deterministic machine, then by definition it is also solvable by a non-deterministic Turing machine in the same complexity in polynomial time. So clearly P is a subset of NP, okay? But the other way around is not known. And this is the millennial problem in computer science and mathematics. So is P equal to NP? This is not known. It's $1 million question. Most people believe that they are not equal. Okay. And then there is the complement of P and NP. The class co-NP, let's define co-P first. So co-P is a set of all problems whose complements are solvable in polynomial time by a deterministic Turing machine. Okay? And if we could solve a problem in polynomial time by a deterministic Turing machine, if we can have an answer to that problem, then we can certainly have an answer to the negation of that problem in the same complexity class. Okay, so co-NP is equal to P. And we have the same problem for co-NP. The relationship between co-NP and NP is unknown. Okay. So co-NP and P, are they equal? So this is unknown. Just like the relationship between P and NP is unknown. Okay, and then there's a class of the class of space complexity, P space. P space. So this is the set of all problems that can be solved by deterministic Turing machines using a polynomial time, using a polynomial number of tape cells or spaces in the theoretical sense. Okay? The set of problems solvable in P time. No, actually. Solvable by deterministic Turing machines using polynomial number of cells with respect to the input size. Okay. Okay, so since a non-deterministic Turing machine can only change one cell per time step, machines that use Pn time to solve a problem cannot use more than Pn space. Okay, so that's why we have that NP is a subset of P space. And we will later see that we don't have any problem for space complexity regarding the relationship between P space and its non-deterministic counterparts. Okay. All right. So the next variant of Turing machines that I would like to talk about is called probabilistic Turing machines. A probabilistic Turing machine is a type of non-deterministic Turing machine, but it's not entirely non-deterministic nor deterministic. So the transition function rather behaves probabilistically. Right, so in non-deterministic Turing machines, when we are in state Q and when we read some symbol A, we might end up with several different states. So we might end up in state Q1, Q2, Q3, and so on. QI, okay, and TM. It just says that when we are in state Q and when we read the symbol A, then it's possible that we get in state Q1, Q2, Q3, QI with equal probabilities. And we don't speak in terms of probability in this case for non-deterministic Turing machines. But in probabilistic Turing machines, all these transitions have weights, P1, P2, P3, Pi, such that the summation of each Pi should be equal to 1. So that's the difference between a non-deterministic Turing machine and a probabilistic Turing machine. Okay, so formally, a probabilistic Turing machine is defined in the same manner as a Turing machine, except that that for all Q1, A1 in Q times sigma, the transition function must satisfy we must have that the output of the transition function maps to a rational number, the probability weight of the transition. The summation must be equal to 1. Okay, this is for the normalization. We may assume that each Pi here is a rational number. It could be a real number, but for computational purposes, let's assume that it's a rational number. If a configuration C yields another configuration C prime with probability P, we denote this by C yields C prime with probability P. Okay. And if we have a sequence of configurations, so let's suppose that C0, C1, up to CT is a sequence of configurations such that the probability of Ci yielding Ci plus 1 is Pi plus 1. Okay, for each I. Then we say that Ct is computed from C0 with probability P1 times P2 times Pt. Okay, and of course no Pi can be 0 in this case, so this is non-zero. Okay, and the sequence of yields starting from C0 ending with Ct is a computation of a probabilistic Turing machine. Okay, so unlike in deterministic computation, a single configuration in a probabilistic Turing machine can yield various different configuration with different probabilistic weights. Okay, So the general configuration of a probabilistic Turing machine can be seen as a probability distribution over basis configurations C1 through Cm. So at any stage, the total configuration of a probabilistic Turing machine can be seen as a probability distribution is denoted by the probability distribution P1 C1 plus P2 C2 plus PM Cm. And here each Ci is a basis configuration. So this means that the probabilistic machine, at any stage t, the probabilistic machine is in basis configuration Ci with probability Pi. Okay, and this defines a vector space. If each Ci defines a basis configuration, then this defines a vector space. We call this vector space the configuration space. Okay, so a general configuration can be thought of as a linear combination in the configuration space. Okay, where the probability factors, the coefficients, all add up to 1. All right. So let's go back to our earlier example in the previous video, and let's try to solve the same problem using probabilistic Turing machines. Okay, so the example was to find whether or not the given input contains symbol 1 in the input. Okay, so example, given an input string find whether or not the input contains the symbol 1. So we do this by using probabilistic Turing machines. Now, the only difference we have now is the definition of the transition function. The transition function will be non-deterministic, having probability weights for each transition. Okay, and since this is a probabilistic machine, it can give us false results. So we may have maybe false negative and false positive results. That is to say, despite that our input string contains a 1, the machine might still give a false negative result and say that that it does not contain a 1. Okay. So this is due to the fact that the machine is probabilistic. It can always give us false results. All right, but let's not consider this in this example. So the transition function sigma will be defined the following way. Again, the columns define, each column will define the input symbol that we read, and each row will define the state of the machine, the current state of the machine. So the states will be, we have QI, initial state, we have QL, and QR. And our input symbols are 0 and 1, This is our alphabet, and then we have the N marker symbol, just used for the sole purpose to denote the end of the input string. Now, if we're in state Qi, and if we are reading 0, and let's also suppose that we're starting reading the input string from the midsection of the string, okay? So the computation starts with 50% of the time. The tape head will move to the left, and 50% of the time it will move to the right. So let's show this by, if we read 0, then so 50-50 will go left, and 50-50 we will go to the right. So with probability 1/2, we change our state to QL, and then we move the tape to the left. But with probability 1/2, we change our state to QR, and we move the tape head to right, one step right. Alright, so if we are in QL, if the current state is QL, with probability 1, we want to go to left. With probability 1, we remain in the same state, and we keep going to the left. Okay. If we are in QR, okay, and if we read 0, we keep looking to the left. We keep looking to the right. So with probability 1, we remain in QR, and we keep going to the right. At any stage of the computation, if we come across with a 1, then we are done. We just accept the computation. So with probability 1, we accept Q accept. Okay, with probability 1, we switch to Q accept. Here again, with probability 1, we switch to Q accept, QA. Okay, and if we fail seeing 1 after we finish looking the input strings, okay, then if we see the N marker, then that means we haven't seen any 1, so we have to reject it. With probability 1, Q reject. Okay, so we assume that the tape head is initially placed on the midsection of the string. So that means if we have 50% of the time the machine goes to left, and 50% of the time the machine goes to right, and that means our machine will examine N/2 plus 1 tape cells. So it will give us the correct answer more than half of the time. Okay, so in the worst case scenario, the machine will go through N/2 time steps. Okay, so this is how we solve the same problem with a probabilistic Turing machine. Okay, so now we turn to quantum Turing machines. All right, quantum Turing machine. So before giving the definition of quantum Turing machine, we want to generalize the notion of computability to the domain of quantum computers. So classical Turing machines rely on classical mechanics, okay? Because the mechanics of Turing machines relies on the Newtonian physics, right? So the tape head moves right, it moves to left, it writes some symbol, erases some symbol from the tape head. So the mechanics just, it works under the rules of classical Newtonian physics. But we also want to allow in our computations rules of quantum mechanics. Okay, so that means we need to extend the notion of computability on the domain of quantum physics, quantum mechanics. The Church-Turing thesis, recall that it tells us that any effectively computable function is also computable by classical Turing machines or classical computers. Now, the extended version of this thesis would say something like any effectively computable function can also be computed by a quantum computer, a computer which is quantum mechanical. Okay, so this will be our extended Church-Turing thesis. So we want to extend the notion of computation to quantum mechanics. Okay, and the extended Church-Turing thesis, let me call it CTT, says that any effectively computable function is also computable by quantum computers. Okay, so we want to allow quantum mechanical features in the notion of effective computability, right? So that's our intention. So a quantum Turing machine is a generalization of probabilistic Turing machine. So instead of using probability factors, we use transition amplitudes. So remember, in probabilistic Turing machines, the delta function was defined as, so it receives q sigma and some direction, left, right, stationary, and it maps to some real number or some rational number. Okay, so the transition amplitude function in the case of quantum Turing machines, the transition function will be defined as it maps to, so delta maps to, in this case, complex numbers. Okay, a set of complex numbers. Which we call the amplitudes of the transition provided to us. Okay, so a quantum Turing machine, let's define it. A quantum Turing machine is defined exactly as a probabilistic Turing machine, except that for any, so is a PTM, except that for any Q1, A1 in Q times sigma, the summation of the modulus squared of the amplitudes should be equal to 1. So Q2, A2, direction, and this is an element of Q times sigma times left to right stationary. The modulus square of delta Q1, A1, Q2, A2, D is equal to 1. Okay. And similar to a probabilistic computation, a general configuration of a quantum Turing machine is a linear combination of the basis configurations. So if C1, and let's denote it by the ket notation, C1 through Cn are basis configurations, then a general configuration of a quantum Turing machine is a linear combination alpha 1 ket C1 plus alpha n ket Cn. Okay. So we may consider these basis configurations as an orthonormal basis of a Hilbert space. So a general state of a quantum Turing machine is a superposition of basis states. Okay, it's a unit length vector in the configuration space. The transition amplitude, the transition amplitude function, determines a linear mapping, as a matter of fact, in the state space, which is expected to satisfy what is known as well-formness conditions. Okay, so the transition function, the transition amplitude function, determines a linear mapping, function delta, let's say, determines a linear mapping U delta, okay, which is expected to satisfy what we call the well-formness conditions. Well-formness conditions, I'm not going to give them here, but you can look at Gruska's book, Joseph Gruska, quantum computing book, and he explains these conditions in detail. Essentially, these conditions ensure that the transition, the mapping U delta, is a unitary mapping, is a unitary operator. Okay, so that's what it means. So the quantum Turing machine works slightly different than a probabilistic Turing machine. Instead of carrying out one of the possibilities, okay, a quantum Turing machine can perform all the operation and can enter a superposition in a superposition state. And then when we measure the computation in the end, the state of the machine collapses into a single state. Okay. But as long as we don't measure it, we get to observe these interference and superposition effects on the input tape. Okay. If we measure the tape content at each stage, at each computational stage, then there's no difference between a quantum Turing machine and a probabilistic Turing machine in this case. Okay, and they would be the same. The difference appears when we don't measure the state of the machine at each stage. We just measure it once at the end of the computation. Okay. Okay, so let's try to solve again the same problem using this time quantum Turing machines. The problem is the same. So given an input string, we want to determine if the input string contains the symbol 1. Okay. So we solve the same problem using a quantum Turing machine. So we have the same states, Q initial, that is Qi, QL, QR, Q accept, and Q reject. Okay. The input alphabet, again, let's assume that it's the same. It contains 0 and 1. Delta is defined pretty much similar. Okay, so initially we start from the mid-section of the input string. If we read 0, we want to go left and we want to go to the right at the same time, simultaneously, with equal amplitudes. So that means with amplitude 1 over square root 2, okay, we go to state QL, and we move the tape head to the right. And then with the same amplitude, 1 over square root 2, I have not so much space here, but I'll try to write. With the same amplitude, we go to state QR, and we move the tape head to the right. Okay. Oops. QR, go to right. Okay, so if we are in QL and we're reading 0 with probability amplitude, with amplitude 1, I shouldn't call it probability. With amplitude 1, the machine will be in state QL and the tape head will move to left. And if we are in QR and if we are reading the symbol 0, then similarly with amplitude 1, we'll remain in QR, the tape head will go to the right. If we read 1, in any case, at any stage of the computation, we're going to accept the input QA with amplitude 1, QA. And if we read the N marker without coming across any 1s, so that means we need to reject the input. Q reject. Q reject. Okay, so note that we don't start the computation in this case by moving either to the right or left. No, we rather move left and right simultaneously. Okay, so let me give an explicit example, and I'm going to write the entire computation and how one configuration yields another. So let's assume that the input is suppose that we have 0, 0, 0, 0, 0, 1, 0. Okay. All right, so the computation of the quantum Turing machine will look something like as follows. So we start in the midsection. Okay, we have the end markers here. So hashtag 000, and then we're starting from this position. The tape head is here. Okay, so that means we are in QI. The next symbol that we will read will be 0, and this is the remaining string. So 0, 1, 0. Okay, and then we have the hashtag and marker. So we have this configuration. Okay, cat this, and then this yields a superposition, right? Because the input that we're reading is 0, so we will have this option. With amplitude 1 over square root 2, we have cat. So with this amplitude, we go to left, and then we change our state to QL. So that means hashtag 00, our state will be QL, and then we move to the left. So that means we will have 00010 hash. Okay, plus. So the next element of the superposition is going to the right. Hash. In this case, we have 0000. We are in Q right. Q right. 0, 1, 0 hash. I didn't know why I keep calling hashtag. This is just a hash symbol. All right, anyway. All right, so we have, from this configuration, we have 1 over square root 2. So we're reading 0 here, and we're in state Q right. Okay. We will have 1 over square root 2 hash 0. All right, so yeah, so first we're going to evaluate the left-hand side, this part, okay? So 0 QL 0 0 0 0 1 0 hash plus, then we will evaluate this 1 over square root 2 hash. We keep moving to the right, so we have 0 0 0 0 0 QR 1 0 hash. And then this yields, we're still in the superposition, one over square root 2 hash QL 0 0 0 0 0 1 0 hash plus, and finally we evaluate this part. So we're in state QR and we're reading 1. That means we're going to accept this. We are in the accept state. Okay. And we end this computation here. Right? All right, so this is very messy. I mean, even a simple task like this requires enormous amount of detail. But this is still a legitimate model of quantum computing. So quantum algorithms could either be defined in terms of the circuit model or abstract model of computation, that is, quantum Turing machines. But it's more convenient to use circuit model when implementing quantum algorithms. Okay, but let me give another example. We often use the Hadamard transform in the circuit model. Okay, so let me show how we use the Hadamard transform by implementing it on a quantum Turing machine. Okay. Implementation of Hadamard transform, Hadamard tensor n, and n qubit Hadamard transform by quantum Turing machines. Okay. All right. So we basically want to transform each symbol 0, right? So all zeros will be transformed into a state ket plus, right? And we transform each one into ket minus. So we have a 0, 1 sequence in the inputs. Whenever we encounter a 0, we will transform that into a superposition of 0 and 1 with plus sign. And whenever we see a 1, we'd like to transform that into a superposition of 0 and 1 with minus sign. Okay, so for this we have only two states, Q initial and Q end. Okay. Okay, so we start with Qi. If we read 0, then we will transform this into a plus superposition state. So 1 over square root 2. Okay. We will write 0. Okay, this is the symbol that we are going to write on the tape head, and we will remain in Qi, and then we move the tape head to left, and then with 1 over square root 2 amplitude, we will write 1. We will remain in Qi, and we go to the left. Okay, so we're starting from the left. We're starting from the leftmost symbol. So this should be okay. So this should be R. Right, we're going to the right. Okay, since we're starting from the leftmost symbol. And whenever we read the symbol 1, we should do the exact same thing, except that we need to change the sign of the relative phase. So we will have 1 over square root 2, 0, Qi, right, and minus 1 over square root 2, 1, Qi, right. And as soon as we encounter the N marker, then we're done. Okay. Right, so this is how we implement an n-qubit Hadamard transform with a quantum Turing machine. Okay, as you can see, it's kind of complex, more complex than implementing a quantum circuit model. All right, so you might be wondering, well, does that add any power? I mean, do quantum Turing machines solve more problems than standard Turing machines? And the answer is no. They're all equal power. I mean, quantum Turing machines solve exactly the same class of functions as um, classical Turing machines and probabilistic Turing machines. So in terms of computational power, they're all equal. Okay. Um, of course, there's this reversibility condition in quantum Turing machines, and that's ensured by the well-formedness condition um, of the operator defined by the transition amplitude function. But we can also make any Turing machine, any classical Turing machine, reversible by adding extra work tapes and output tapes. Okay, so with a 3-tape classical Turing machine, we can implement a reversible Turing machine. So this was proven. In terms of computational power, there's no difference. Okay, so quantum Turing machines have exactly the same power as classical Turing machines and probabilistic Turing machines. So let me write that down. In terms of computational power, quantum Turing machines, probabilistic Turing machines, and deterministic Turing machines are equivalent. Okay. We can simulate a quantum Turing machine using a standard deterministic Turing machine. Maybe not effectively. I'm saying maybe because possibly not effectively, because we have the Shor's algorithm, right? So there's no known polynomial time algorithm for integer factorization, but with quantum computers we can solve this problem in polynomial time. So maybe standard Turing machines can only simulate quantum Turing machines in exponential time, but theoretically they solve the same class of functions. Okay, so they both cannot solve the halting problem. All right, so one last thing I'd like to note is the existence of a universal quantum Turing machine. So we say that a Turing machine is universal if it can simulate the computation of any given Turing machine on any given input. Okay, and so we know that a universal Turing machine exists. This was proven by Alan Turing, of course, but this is also true for the quantum case. David Deutsch in 1985 proved the existence of a universal quantum Turing machine which can simulate other quantum Turing machines on an arbitrary given input with arbitrary precision. Okay, so in the next lecture we will talk about complexity classes. So I'll see you in the next video.